Hello everyone. So welcome back to our latest lecture session. So we were discussing, I believe, precipitation and dissolution, and in the first session, or relevant session, we looked at the applications initially, and then I believe we moved on to looking at, I guess, why kinetics play an important role in this particular aspect of precipitation, right? And then we moved on to looking at the four major aspects or stages, pardon me, that are involved with precipitation. And again, there is a particular reason why we are going through each stage, because later on, let's say when you want to either promote precipitation or let's say hinder precipitation, you need to tinker with some of these stages, right? So again, that's the reason we are going through these stages, and the stages I believe we looked at were nucleation, and what is it now? The next step obviously would be crystal growth, and then agglomeration, more or less accumulation, right, or coming together, and then ripening, I guess. So we are done with or we started discussing about nucleation. So nucleation, I guess you have the solid being what do we say, formed, and more or less they are at the nanoscale. So I guess the smallest particle that you can call to be a solid, and I think the term we are using in this context is nuclei, right? So the nuclei are formed obviously, right? I mean, this is terminology again. They are more or less nanoscale, right? And then what's the aspect that we need to consider here, I guess, right? So is just saturation good enough? Saturation good enough for your nucleation to go through? No. Again, why is that? I think that's because the rate of your nucleation is equal to k times s minus 1 to the power of m, right? So just say if s is 2 or so, right, even though it is saturated, you see the rates are going to be relatively less, right, or not good enough for your particular nucleation to go through now. Again, nucleation as in we are considering that there are no other solid phases present in the solution or suspended in the solution, right. So here it's from scratch, and so obviously for that what do you need? You need supersaturated solutions when S is greater than or around 100 or 1000 or so, right. And again, I think we talked about the order of M, I think 3 to 8 or 3 to 9, I guess, right. So as you see, once you have the supercritical saturation as an S in the order of around S is in the region of about 100 or 1000, let's say, then you are going to have more or less what we say rapid nucleation going through, right. Again, that's because M is relatively high. So I believe we have a relevant figure here. So here we have rate of nucleation, right, and here is what do we say, degree of saturation. C is the concentration of the relevant ions in solution, and Cs is the saturated concentration of those particular ions, let's say. So S here we are saying is the degree of saturation, right, and also keep in mind we looked at saturation ratio 2 earlier, right. I think that was equal to Q by KSO, right, to the power of 1 by X, right. Again, degree of saturation here. So obviously when it's less than 1, what does it mean now? C is less than Cs, right. The current concentration of the relevant ions is less than their saturated values, right. So this is going to be under saturation. Yes. Thus obviously if the solution is undersaturated, there is going to be no nucleation as such that is going to go through. So that's what you see here, in this region you see that there is no nucleation here. So this particular dotted line is just to for our particular understanding of where the S equal to 1 lies, right. So you see that even when S is greater than 1 in this region where we say it's oversaturated, right, S is greater than 1 or C is greater than Cs, right. When S is greater than 1, C is greater than Cs, but you still see that the solution doesn't favor or promote nucleation. Again, this is from particular graph, I guess, right. Still you see no nucleation here, but only when you are within the supercritical saturation zones or when you reach the supercritical, right, S critical, let's say, right, and you see a rapid increase, more or less like a switch turning on or off. That's what we were trying to understand. Why is that? Again, because the order, right, order R equal to K S minus 1 to the power of M, the order is relatively high. So once the conditions are favorable, it takes off, it as in nucleation takes off, right. So that's something that we looked at, yes. So obviously the next step would be what we say, now you have just these what do we say, independent what do we say, nanoscale solid particles, the smallest particle that we could call as what we said now solid, right. So next step obviously is the crystal growth, right, and let's look at that, right. So crystal growth, I guess, yes. So here let's say there are aspects involved. So obviously first let's look at what's the rate of this particular crystal growth. R equal to K times A is the concentration of your surface area, let's say, right, into S minus 1 to the power of n. N is usually 1 and sometimes also equal to 2, right. So here let's understand which aspects play an important role here, right. So earlier if you remember that S with respect to nucleation, what was the equation? R equal to K times S minus 1 to the power of m. M is around let's say 3 to 8, right. This is for nucleation. So here S plays an important role, right, and why is that? Because the order of the relevant set of variables is relatively high, but here the order is only either 1 or 2, right. So actually what plays a much more important role is the size of your particular particles here. Here A is the surface area concentration here, right. A is the surface area concentration here, and that's why as you see here again the saturation ratio does have an effect, but here we have an important new variable, that's the surface area concentration here, right. So the greater the area available for your particular solid, right, that would mean the greater the rate of your crystal growth, right. So if you want to promote precipitation at this stage, what can you do? You can either add a lot of your particular what is it now compound or the solid to increase, yes, but the effect will be relatively less because the order is 1 or 2, right. Or obviously you can also try to add smaller size particles, right, which will have a greater surface area, yes, or obviously even adding more solids will have a net effect or have a net increase in the surface area. So it's better off that you try to what do we say, tinker with A rather than S, but more or less, and depending on the relevant size of the particles, they obviously are interrelated, right. Again, so if you want to promote crystal growth, the surface area concentration, right, is an important aspect here, right. So again, that's one aspect that we need to consider. So let's move on to the next aspect, I guess, and then we hear the next stage in your particular precipitation after nucleation and then crystal growth is now going to be agglomeration, as in accumulation or the solids coming together now, right. So here what is it that means now? How is it going to affect your particular precipitation? So keep in mind that the relevant equation is still the same, what is it now? R equal to K A S minus 1 to the power of m, right. And now let us say as the size of the particles keeps increasing, right, A keeps decreasing, right, the surface area concentration keeps decreasing now. So in effect, what does agglomeration or the stage of agglomeration lead to? It leads to a decrease in the relevant rates, right, because the size of the particles increases, and as you see, as size increases, right, the surface area concentration decreases in your particular solution, yes. So obviously that's one particular effect of agglomeration, yes. So let's move on to the last stage. So it's ripening. I guess you do have the natural corollary of a fruit turning ripe, right. So in the same case, I guess that's how I tend to understand this particular stage anyway. So ripening here, it more or less means you have formation of, and this, keep in mind, is the last stage, right. And if you remember, I think the example for Al3 plus or something like that, right, it falls down the ladder, different solids. So the last stage would be the most insoluble form of your solid, right. So we know that this is how the precipitation or the kind of solid changes. So the last form, let's say this is solid form 1, which will be relatively soluble, right, relatively soluble, and solid 2, let's say, which is relatively insoluble, and then solid 3, I mean assuming that there are 3 solid phases that Al3 plus can precipitate in the form of, right. So here solid 1 is most soluble, and that is why it is going to be formed first, then solid 2 which is relatively insoluble, and then solid 3 which is the most insoluble of the 3 solids, right. So, again keep in mind that this is the order in general obviously that it proceeds, right. So, your most soluble solid obviously will be formed first, right. So, that is what it means here, the most soluble solid would form first, right. Again, so here what is it now? We have the formation of relatively insoluble what do we say, solid species, I guess, or solids, right. Formation of relatively insoluble solids, right, a transformation of the relevant solid into more insoluble forms. That might be a better understanding, guys. So, transformation of the solids into relatively more insoluble forms, right. So, that is what we have here. There are two cases here. I think one is the Oswald ripening, right, as in your solid becomes more insoluble more or less due to the increasing area or surface area or increase in the particle size, you know. So, the effect of particle size here. That is more or less one particular case, right. We are going to look at the other case too, but before we move on, we have relevant equation here. So, here we have the solubility constant of, let us say, the smaller particle, you know, KSO, right. Let us just try to we have a relevant equation here. Let us just try to understand this particular system here. So, log KSO, right, and what is KSO? Obviously the solubility constant which I sometimes call the solubility product of the relevant smaller particles. KSO at infinity, time at infinity means it is for large particles, right. So, that what it means, KSO at infinity is the equilibrium constant for the larger particles, right. S is the molar surface area, area per mole, right. Again we have a new term here, this is not the saturation ratio, keep that in mind please. You know, we have these are relevant variables. So, molar surface area or area per mole, right. So, obviously that depends on the particle size, right. So, the lesser the particle size, the greater the S, right, and that is what we need to understand here. So, obviously here what can I understand here, right, what is the effect of S on KSO now. So, the smaller the particle size, right, this greater the value of S, right, the area per mole. The smaller the particle size, the greater the area available of the solid per mole, right. So, here obviously the smaller the particle, the greater the S, that more or less translates to a higher value of KSO, right. So, the smaller the particle size, the greater the value of this area per mole or molar surface area, right, molar surface area, right. So, that more or less means a higher value of KSO, right. And what does a higher value of KSO more or less translate into now? So, obviously KSO, let us say, you know, let us say for one particular example, AlOH thrice solid in equilibrium with Al3 plus and 3OH minus, right. So, obviously KSO for this particular case, what is that now? Activity of Al3 plus times activity of OH minus to the power of 3 by activity of AlOH thrice solid, but as we know activity of a pure solid is 1. So, that is why we are not going to have that here. So, obviously here let us just understand what we are up to. So, the smaller the size of the particle, the greater the value of KSO. So, if KSO is higher, right, what does that mean? The greater the concentration of the relevant what do we say cations or anions, right, or in this case the metal Al3 plus. So, again what does that mean? The smaller size particles are relatively more soluble, right. So, that is our particular understanding from here. I think we have a decent aspect here or graphic here. Small particles, larger S, right, that means higher KSO, which as we looked at in this particular example means it is more soluble, right. Again small statistic, as in when the surface area effect or you know the concentration becomes apparent, it seems around 10 micrometers, right. So, that is one particular aspect that you know you can keep in mind, I guess. So, let us move on. Okay, let us just summarize, I guess, before moving on to the other aspects. So, we looked at nucleation, right. and we saw that this greatly depends on, what is this now? This is the saturation ratio. Saturation ratio S here, that's different from the S here in this particular equation. And then we looked at what is it please? Crystal growth, right? Crystal growth. So that depends both on, what is it now? The surface area concentration, or more or less, let's say I can even call it molar surface area in a way, and also the saturation ratio, right? Crystal growth. And what happens in agglomeration now? Due to increase in the what is it now? Increase in particle size, A decreases, thus rate also decreases. That's what you see in agglomeration, right? And obviously the last aspect was ripening, where I believe I missed the second aspect, which I am going to discuss now. One aspect is, as the size increases, as just what we saw now, I guess, right? So what do we see now? The size increases, right? The solubility decreases. Right now in this particular equation and such, what did we see? When the size is lesser, the solubility is greater, right? So more or less, that what does that mean now? When the size increases, you know, you have more insoluble forms of the solid, right? So that's the Oswald ripening. So the second case is when you have a change in structure, or the way your particular atoms or molecules are arranged, right? So in general here, I guess, let's say an example will be transformation from amorphous to crystal growth, let's say. So in general, amorphous is more soluble and crystal growth is less soluble, right? So obviously crystal structures relatively more stable than compared to the amorphous, what do we say, arrangement, let's say, right? So obviously what does that mean now? The less stable one is formed first, as in amorphous form is formed first, and later, given enough time, it will transform into the crystal structure, right? So that's the second case of what is it now? Ripening. One is due to the effect of particle size, the other is due to the transformation in the arrangement of your particular atoms or molecules here, right? And with that let's move on. So here one aspect is, how can I control the precipitation, right? How can I control the precipitation now? So obviously that's the reason I just listed the various aspects here. So here we have different aspects. Let's say we are talking about promoting what do we say, precipitation, let's say. So which is the case when you want to remove heavy metals or such and so on, let's say. So how can you do that now? As we listed it in case of nucleation, what can you do? You need to increase the value of the saturation ratio, right? So you can increase the effect of what is this particular S, right, saturation ratio, increasing that. As we see in that nucleation, when S is in terms of 100 or 1000, you know, that's one particular case, or even in your particular crystal growth, S minus 1 to the power of n. So increasing saturation ratio is one aspect. So obviously another aspect is increase in A, right? What is this now? Surface area concentration, right? And how can we look at this particular aspect? How can we improve this now? We can improve that by just increasing the concentration of your solids too will end up increasing the area available per mole, let's say, right? Or what else can you do? By decreasing the particle size, because as you know, the smaller the size of the particle, you know, the greater the area available per unit volume, let's say, right? So that's one particular aspect. So how do you want to you know, inhibit or decrease or slow down precipitation now, right? So let's say you have scaling in your evaporative cooling towers, or in your at the surface or your membranes, right, or at the membranes and so on. So how do you do that now? Again, one aspect, right? How can I go about that now? I can decrease S to less than 1. What does this mean? So I can create under saturation conditions, right? So how can I do that now? How can I, you know, make the what is it now, or bring down the value of S, right? So for example, keep in mind that, let's say for our example, let's say, you know, we had Al3 plus and OH minus. So how can you bring down the free metal concentration, right? So you can bring down a free metal concentration by how now? Adding a complexing agent, a ligand, right? So if you add a ligand, you know that the free metal concentration is going to be relatively less, right? And then obviously the saturation ratio is going to be less than, or decreasing. So depending upon how much of your complexing agent or ligand you add, the free metal concentration can decrease to less than 1, and that is one particular way. So we can add what do we say, ligands, or the relevant ligands anyway, right, or the complexing agent, right, complexing agent. And what else now? So the second aspect that you can look at is obviously you need to have or you can create turbulent conditions, right. So at that particular case, when you create turbulent conditions too, let us say at the surface of your membrane, let us say nanofiltration or ultrafiltration membranes, you can create turbulence, right. So at that case too, you are going to be able to decrease the value of the saturation ratio. So that is one particular aspect, right, and that is with decreasing the saturation or creating under saturation conditions to inhibit the precipitation. And one particular case where we look at, or we just looked at, was scaling on the membranes. Obviously the second aspect is the scale inhibitors, I guess, right. As in, we can try to limit the two stages. Let us say, what is it now? We can try to inhibit nucleation, right, the initial step or trigger that is required, or we can inhibit crystal growth, let us say, by adsorbing onto surface or such, right. So again, there are different ways to either promote or what is it now, inhibit precipitation. So that is one particular reason why we looked at the 4 stages, to have a better or deeper understanding, right. So let us move on. So here now, let us say until now we have talked about the relevance of kinetics, right, in precipitation and dissolution, and we say that at least in precipitation, right, the relevant reactions are relatively slow. So in general, first the most soluble form of the solid is formed first, and then it is usually a very slow process to reach the true equilibrium when the most insoluble form of the solid is formed, right. Again, kinetics, we looked at the different stages and the relevant role of the kinetics as in the different rates at different stages, right. So now obviously, let us say if the system reaches equilibrium or even the metastable equilibrium, right, either true equilibrium or the metastable equilibrium, as in even when you have one controlling solid, how do I find the relevant concentrations of the relevant what is it now, metals or such, let us say, right. So how do I go about that now? So obviously, I think we talked about this solubility constant, or which as I call it, the solubility product. So we have this KSO or KSP, right, depending upon the type of source you look at, either KSO or KSP. So what is it we talk about here? Let us say, I have a solid here, AlOH thrice solid. So it is the solubility product, right. So it is more or less the dissolution reaction that we always write when we refer to KSO or KSP. So that is going to be Al3 plus 3 times OH minus. So obviously KSP or KSO will be equal to what is it now, Al3 plus times OH minus to the power of 3 by the activity of AlOH thrice the solid, right, but activity of the solid is equal to 1, right. So that is why we end up with KSP is equal to the activity of the products raised to their stoichiometric coefficients, right. Again, KSP, I guess. So that is what we have here. So this is what how would you go about understanding or solving for a system at equilibrium? You obviously need to have the knowledge about the relevant solubility constant or the solubility product, right. So again, let us say given a particular system, let us say aluminum, or in this case aluminum, let us say, can you directly use this particular equation? For example, let us say assume you have the pH, right. Consider this case where you have the pH of the solution, let us say, right, and let us say the K solubility product for this particular equation now, So if someone asks you, can you solve for Al3 plus, right, the free metal concentration, do you think you are ready to solve for it? Not really. Why is that? Because from our background we know that the relevant reactions, as in acid base, maybe not acid base in this case, so aluminum will form complexes, right. So all the complexation reactions are also obviously going to occur simultaneously, and they are also going to reach equilibrium within or before the solid is formed, right. So at this equilibrium or the metastable equilibrium for a particular solid that we are considering, not only will you have the precipitation or the relevant dissolution, you will certainly have the complexation reactions too. So you can't directly just apply, okay, I know the pH, so I know the OH minus, I know the KSP, and I can calculate Al3 plus, right. That is not how it is going to work. Why is that? Because Al3 plus is also going to be in equilibrium with not just the solid, it is also going to be in equilibrium with the different complexes, as in, so the Al3 plus, let us say, is not only going to be in equilibrium with your solid, but at the same time it is also going to be in equilibrium with your complexes, right. So obviously you can't just ignore, you know, one set of your particular what do we say species and just go ahead with the particular solution for the solid, right. So here try to understand what we have been doing until now. Initially we talked about acids and bases, which more or less is, let us say, a foundation for our class other than the fundamentals obviously, and then the next logical step was complexes, and the next logical step is now solids or precipitation, right. So again all the three aspects, you know, occur in conjunction, so that is something you need to consider. Okay, so with equilibrium 2, what are the conditions that I need to keep in mind, let us say, when I solve for precipitation, let us say. So obviously we are talking about precipitation. So what does that mean? First aspect is that a solid needs to be present, right, or should be present or exist in the solution. So that is obviously one what do we say underlying phenomena that you need to look for, right. When you are solving for equilibrium, you need to first check whether you have a solid that is precipitated out or not, right, otherwise it makes no sense. So we are going to look at this particular aspect later on again, and we will look at why it is important. And obviously just having a solid is not good enough, so it should also be the case that the solid is at equilibrium, either equilibrium or metastable equilibrium, right, with the aqueous species, right. So first obviously the one condition is that what is it now, the solid should be present, and then that the solid should also be at equilibrium with your relevant species that are dissolved in the water, right. So these are two aspects that we should certainly consider now, right. So let us move on, I guess. So model, I guess. So in general until now, how have we solved for systems at equilibrium now? We came up with this conservative quantity. What is a conservative quantity, right? You know, that we looked at, that is the component. So we defined components and we solve for the relevant aspects, right. So in this case too, we are going to follow the same approach. What is that now? The component balance approach, right. Yes, but here what is the key, I guess, similar to when we had the gaseous phase and the liquid phase. So earlier, if you keep in mind, you know, we had the aqueous phase, and it was, you know, we solved for cases when it was in equilibrium with the gaseous phase, right. So we identified some component, right, x total, I think, is equal to x total in the aqueous phase plus x total in the gaseous phase, right. So similarly here too, we are going to have a case where aqueous phase and the solid phase, they are at equilibrium, right. So the x total is now going to be x total in the aqueous phase plus x total in the solid phase, right. So we are going to take this further, but I guess it needs some more time, which we are short of right now. So we are going to go through with you know, understanding how to solve for your particular system first by hand. You know, first you are going to understand the basics, right, and then obviously we are going to look at the applications with respect to Vim intake, right. And so I guess with that I will be done for today's session, and thank you.